Welcome to your Easter revision course on physics. The big calculation you will carry out today is to find out the mass defect in a nuclear reaction and then use Einstein's famous equation E is equal to mc squared to calculate the energy released. Later on in this course we will do the opposite, where we look at the formation of new particles in a particle accelerator, where the energy of the colliding particles produces new matter. The processes of fission and fusion will be explained as a means of obtaining energy from the nucleus. We will also explore the variety of exotic new particles that have been discovered using particle accelerators. There are so many of these particles, it has been called the particle zoo, and required a brilliant physicist called Murray Gell-Mann to bring some order to this collection of particles by developing the famous Standard Model. So enjoy this course where I take you on a journey that is both weird and exciting. So welcome to Modern Physics. We're on lesson number 7, nuclear energy calculations. And we're going to use a very famous equation here. The famous equation that everybody knows, E is equal to mc squared, which was put together by somebody called Albert Einstein, who everybody knows. So let's go to your notes on this and let's have a look at Einstein's equation. So what did Einstein say? Well, Einstein said this: energy is conserved in nuclear reactions. It doesn't change from the start to the finish. But Einstein said mass has to be considered a form of energy when you're looking at your nuclear equations, because in nuclear equations mass changes into pure energy like photons, gamma photons. I'm not talking about burning mass. There's a lump of coal, let's say, a mass m, and let's say we burn that and it turns to ashes. Well, the chemist will tell you that the mass of the products is equal to the mass of the reactants. In other words, the mass afterwards and the mass before is the same. But what Einstein said was, we're not talking about burning it, we're talking about completely vaporizing it. We're talking about turning that mass there into pure energy. Massless photons that travel at the speed of light. Gamma photons that have a huge amount of energy. So if I take that mass there and I completely vaporize it, so there's 0 kilograms of mass left, and I've turned that into pure energy. Well, the amount of energy you get out of even a small amount of mass is enormous. He came up with his famous equation. His famous equation was E equals mc squared. It looks like a beautifully simple equation, but it's actually very complex. We're just going to learn how to use it. So E is equal to mc squared. What does E stand for? E stands for the energy that is going to be produced when you vaporize that mass. Energy is measured in joules. M stands for the mass, and the mass is measured in kilograms. And C stands for the speed of light. Now the speed of light is a very big number, and you can see it's the speed of light c squared, which is an even bigger number. So the amount of energy you get by vaporizing even a small amount of mass will be enormous. It's very hard, by the way, to actually vaporize all the mass. You'll partially do it inside nuclear reactors where you'll turn a little bit of mass into pure energy. But to turn the entire mass into pure energy, that's a very, very difficult thing to do. C stands for the speed of light. And speed, of course, is measured in meters per second. And the speed of light you're going to get in your table book, I always round it off, unless they ask me otherwise, to 3 by 10 to the power of 8 meters per second. So you'll find that in your table book. So if I go to my table book and have a look at that, so you can see it there on page 47. It's called the speed of light in vacuo. That means in a vacuum. That's why we call it C0. And the value is 2.997. It's practically 3, isn't it? by 10 to the power of 8 meters per second. So let's have a look at an example using Einstein's famous equation. Let's have a look at example number 1. It says how much energy is contained in 20 grams of mass. Well, I'm going to use Einstein's famous equation. E is equal to mc squared, and c is 3 by 10 to the power of 8 meters per second. Well, the first thing I've got to do is write down the mass in kilograms. So mass is measured in kilograms, energy is measured in joules. To change that to kilograms, I'm going to divide by 1,000, jump the decimal point 3 to the left, so I get 0.02 kilograms. C is 3 by 10 to the power of 8 meters per second, which you'll get from your table book. But you'll probably remember it because it's such a famous number. And I'm looking for the energy I get when I vaporize 20 grams. Vaporize it so there's no mass left. I'm turning into pure photons that are traveling at the speed of light. My formula is E is equal to mc squared. So you see that formula there. That formula works when energy is in joules and mass is in kilograms. So that's equal to mass 0.02 multiplied by C 3 by 10 to the power of 8 all squared. So I'm going to put that into my calculator. .02 by bracket 3 by 10 to the power of 8 close bracket squared equals, and I get a value of 1.8 by 10 to the power of 15. That's a huge amount of energy from such a small amount of mass, only 20 grams of mass. And of course the answer will be joules. So anytime I use the formula E equals mc squared, energy is in joules and mass is in kilograms. One of the things you have to be very careful of when you do calculations in nuclear energy are the units. We have what are called big units. They're your normal units. The big units for mass, we've already talked about, kilograms. The big units for energy, joules. And what's the formula if you want to work out the amount of energy contained in any mass? Well, then we're going to use Einstein's famous equation, E is equal to mc squared. So I've already done an example on that. That's using the big units. But we're also going to be using small units. Why do we have these small units? Well, if you talk about the size of a proton, its mass is going to be a millionth of a kilogram. If you talk about the energy of a little photon, you're going to be talking about fractions, tiny fractions of joules. So we make up these new units that are more appropriate for the very small size that's inside the nucleus. We've already seen these small units in earlier lessons on modern physics. The small unit for kilogram is the atomic mass unit. We've already said to you that the mass of a proton is about 1 atomic mass unit. And the small unit for the joule, we've also seen that as well. That is the electron volt, EV. And we have these conversion factors that can take you from one to the other. For example, 1 atomic mass unit. You'll find this in your table book. That's 1.66 by 10 to the power of minus 27 kilograms. So I've rounded that up a fair bit from the number that's in your table book. And the electron volt, well, 1 electron volt is 1.6 by 10 to the power of minus 19 joules. So those factors, conversion factors, will allow you to convert from the little units, the small units, to the big units, and vice versa. So you'll find those conversion factors where all your constants are. All your constants are on page 46 and 47 in your table book. So for example, there's the atomic mass unit, U, and there's the full number, 1.6605402 by 10 to the power minus 27 kilograms. Sometimes we'll use the full number for real accuracy when we get down to the very small level of the nucleus. Other times I'll round it off. I've rounded it off, you've seen, to 1.66 by 10 to the power of minus 27. And then if I look at the electron volt, is on page 46. So there's my electron volt there, and I've rounded it off to 1.6 by 10 to the power of minus 19 joules. So there's my conversion factors. So let me do a simple example using the small units. Let me go on to example number 2. It says how much energy in electron volts, they're the little units of energy, would be contained in a mass of 1 atomic mass unit, the little units for mass. Well, the only formula we have for converting mass into energy is E is equal to mc squared. And E is equal to mc squared, that uses the big units. That uses joules and kilograms. So I've got to turn my little units into big units. Right, so the mass is 1 atomic mass unit. I'm going to use E equals mc squared. So I need that in kilograms. What's 1 atomic mass unit? It's 1.66 by 10 to the power of minus 27 kilograms. Now I can use my formula, E is equal to mc squared. I'm going to vaporize 1 atomic mass unit. That's about 1 proton. So it's like vaporizing a proton. So that's equal to m, 1.66 by 10 to the power of minus 27, multiplied by the speed of light squared, which I've rounded off to be 3 by 10 to the power of 8 meters per second, all squared. So I'm going to put that into my calculator. 1.66 by 10 to the power of minus 27, multiplied by bracket 3 by 10 to the power of 8, close bracket. And I get a value of 1.494 multiplied by 10 to the power of minus 10 joules. So obviously when you do E equals mc squared, your answer for energy will be in joules. Now I want to turn that into the small units of energy, which are the electron volts. Well, 1 electron volt is equal to 1.6 by 10 to the power of minus 19 joules. If I'm going to turn that number of joules into electron volts, I'm going to divide by that conversion factor. You're going to divide because you're going to get a lot of electron volts, a lot of the little numbers. So that's equal to 1.494 by 10 to the power of minus 10 divided by 1.6 by 10 to the power of minus 19. So put that into my calculator. I already have that number in my calculator. So I'm going to divide by 1.6 by 10 to the power of minus 19. And I get this very big number that I'm going to write down in scientific notation. I get a number of 9.34 multiplied by 10 to the power of 8 electron volts. So that's the number, that's the amount of energy in the little units of the electron volts. Now we do something with that. We're going to use something called a mega, a prefix called a mega. Mega, you've seen before, is the prefix for 10 to the power of 6. I'm going to take a 10 to the power of 6 out of that. So I'll do it slowly. So that's equal to 9.34. I'm going to break that up into 10 squared by 10 to the power of 6. That's okay, isn't it? Because when you add the powers, you get 10 to the power of 8. 10 squared is 100. So I'm going to multiply 9.34 by 100 to get 934. And you see that 10 to the power 6? I'm going to replace that by a mega. So that's going to become mega electron volts. So what I'm saying is, if I vaporize 1 atomic mass unit, I get 934 mega electron volts. Well, actually, I want to be a little bit more accurate than that. If I used the full numbers instead of rounding them off, I would have found that when I vaporized 1 atomic mass unit, I got exactly 931 mega electron volts. That's the actual number you get when you vaporize 1 atomic mass unit. That's a very famous number. Unfortunately, they didn't put that into the table book, and it can be quite useful. I would actually ask you to learn that and use it occasionally. When you vaporize 1 atomic mass unit, you get 931 mega electron volts. That's very handy. For example, if they gave you a mass, for example, of 5 atomic mass units, and they said how much energy is in 5 atomic mass units in electron volts. Well, do you want to go through all this rigmarole again? Change the atomic mass units into kilograms, then use E equals mc squared, then divide by the conversion factor? Well, if I know that 1 atomic mass unit is 931 mega electron volts, I know that the energy here is going to be 5 atomic mass units multiplied by 931 mega electron volts. So it's going to be 5 by 931. And I get 4,655 mega electron volts. So I'm going to sometimes use that important piece of information. 1 atomic mass unit, the amount of energy in it is 931 mega electron volts. So if I go back to my table here, we have big units and we have small units, and we can convert from one to the other. When I use the big units, you can use E equals mc squared. What about the small units? What formula could I use? Well, if you wanted to work out the energy, you'd multiply the mass in atomic mass units by 931 mega electron volts, and that will give you the energy in mega electron volts. So there you can see in your notes underneath example 2, I've made a big point of saying that 1 atomic mass unit contains 931 mega electron volts of energy. So learn that number. And I've summarized then your big units and your small units. So the information you need to use about big units and small units are contained in that table there. When we're talking about big units, use E equals mc squared. And small units, you can multiply the mass in atomic mass units by 931 mega electron volts to get the amount of energy in the small units. And you've got your conversion factors there. So that summarizes everything you need to know about big units and small units. You need to be very, very comfortable operating between the big and the small units. And if you can do that, you'll have no problem working with nuclear equations. I am continuing with modern physics lesson number 7, nuclear energy calculations. Let's say we have to do a nuclear energy calculation. So we have a series of particles that have reacted. How do I find the masses of all the particles? Well, sometimes in an exam question, they'll give you the masses. So if they give you the masses, obviously take it and go with what they give you. But if they give you no masses, then you have to go to your table book to find those masses. Now, the masses can be given in the big units, which are kilograms, or the small units, which are atomic mass units. In your table book, they give you the masses of 4 particles in kilograms, just 4 particles, not the rest of them. They give me the proton, the neutron, the electron, and the alpha particle. You will find them on page 46 and 47. I've written them down there for you. Notice that I've written down all the decimal places. I put in all the numbers. It's the only time really in physics where I don't round it off, because even a small piece of mass can yield a huge amount of energy. So I'm going to use the full numbers of the masses when I do my energy calculations. So if I go to my table book, page 46 and 47, you can see there at the top of page 46 you've got the mass of the alpha particle. There's your mass, the mass of the electron. There's the mass of the neutron. And then on the next page, I will have the mass of the proton. All the other particles in the periodic table are given in your table book, but they're given in the small units of atomic mass units. You'll find them on page 83 to 90. For example, the first one is hydrogen. Well, actually, you know that a proton is simply a hydrogen nucleus. So P is equal to H11. And its value in atomic mass units is 1.007825. Before, when I talked about the mass of the proton, I rounded that off to 1 atomic mass unit, but that is its exact value. They also give me the mass of the alpha particle, because the alpha particle, as you know, is part of the periodic table. It's actually a helium nucleus. Alpha is equal to He24. So you'll find that there as well. So if I have a look at page 83 in the table book, you will see the values there. So here's Z, atomic number 1, and H11, and its value, as I've already written down on the board, is 1.007825. And what about He24? There's atomic number 2, and there's the isotope of it with mass number 4, and its value is 4.002603. So every element of the periodic table and its isotopes are in there from pages 83 down to 90. So they don't give you any information. You have to go to these pages and find out what the masses are in the small units. Now, one value they don't give me in here is the mass of the neutron in atomic mass units, which I think would be very useful. We obviously have it in kilograms. I could work it out in atomic mass units myself. The reason it's not there is because a neutron would not be part of the periodic table. There's the conversion factor between atomic mass units and kilograms. I've given you all the numbers, all the decimal places there, because I want to do this very, very accurately. So if I want to work out the mass of the neutron, mn, in atomic mass units, I will get the mass of the neutron in kilograms, which is 1.674 927 28 by 10 to the power of minus 27. And I'm going to divide it by its conversion factor, which is 1.6605402 by 10 to the power of minus 27 kilograms. And I'm going to put that into my calculator. The 10 to the power of minus 27s cancel. So when I put that into my calculator, I'm going to divide that number by that number. And when I do that calculation, I get an answer of 1.008664 atomic mass units. So I'm going to put that in here into my table, 1.008664 atomic mass units. That's the mass of the neutron in atomic mass units.